I'm Alfonso Perez. I come from the Biomedical Informatics group of the Technical University of Valencia, the same as David Moner yesterday. And I'm going to talk about a generic data mediating architecture that we developed for decision support system. So next, please. Okay, well, it's a little summary of what I'm going to talk. Before talking about the architecture, I'm going to introduce a little why we needed to develop this. And well, next, please. Next, please. Well, in 2008, we started developing a computer decision support system called Curiam, and here we took the first steps to manage the data at a generic level. Curiam connected to database through a generic data framework. So next, please. In the next years, we developed an HL7 CDA wrapper that make use of it provided the CDSSs with standardized clinical documents as inputs and outputs. These documents followed an HL7 CDA template, as you can see here in the diagram. So the main workflow here is well, the semantic interpreter loaded the CDI input document and through a binding file look for the corresponding attribute that the inference engine needed. So in our case, the inference engine was a yes engine, but it could be any type of engine as rules. And after the engine execute the rule, the data was passed back to the semantic interpreter, and this interpreter created a CDA output also following the HL7 CDA template. So yeah, next please. We also worked in a Proforma data collector. This was an ad hoc data collector, so it only works for this engine, but this allowed us to Proforma to create or to load the data sources data from different data sources through a configuration XML. So next, please. Next, please. Yeah. This, when we were working with the Proforma engine, we realized that most of the computer interpretable guidelines engines work with a few data sources, or well, a limited quantity of data sources. So we propose a solution as a mediator architecture able to grab the data for not only the Proforma engine, but for any CDSS. So next, please. Yeah, we call this architecture clinical decision support data mediator, and the main attributes are it's a lightweight and modular data mediator, and it allows the clinical decision support systems to decouple their implementations from the necessities of the data. And its one requirement was that it was designed as a non-invasive data wrapper, because we didn't want to modify the already existing CDSSs. Next, please. So where do we have to put this mediator? Well, as the name explains, it has to be between the CDS system and the data sources. Here you can see in the diagram the most common way of using the mediator is in the path A. It's between the CDS system. The CDS system will make a request, and the CDS data will transparently make that request to the data source specified. This mapping needs to be specified in the data mapping module file that you can see here connected. One thing that we don't manage is the data at semantic level. So if you want the semantic interpretation of the data, you have to use a semantic mediator or semantic system. So in the paths B and C, you can see how could be connected the mediator with a semantic tool, providing a complete data integration for the CDS system. So next, please. Yeah, I'm going to talk about a little about the architecture, how this system is well created. Um, the architecture is divided in two independent modules. The execution engine module, which is the module that is going to be related with the CDSS engine, is the module that is going to give mm, the ability to the CDSS to load different types of data, and the data loaders, which
Alfonso, we are losing your sound, and
oh
I cannot give it more volume, so you really need to speak,
okay.
I think, more closer to the
Yeah.
microphone. Yeah, thank
Sorry.
you. Yeah, now.
But I didn't realize that I was, yeah. Okay. So, yeah, the execution engine module, which allow the preloaded and, well, several functionalities as preloading data as before the CDSS execution started, and the data loaders module that, well, define the data source that is going to be accessed. We created this architecture separated because and we want to provide the functionality of extending these two modules independently. So if you want to add more data loaders, you don't need to change the execution engine module. So the CDSS that already implemented the mediator can use the new data loaders without changing anything. So well, the data loaders are the data type specified in the data loaders is specified by a value option. So next, please. Yep. This value option, as I said, specifies the types of data that can be loaded by the data loaders, meaning that well, here you can see there are four types of value options. Um, this value options specifies how where is going to be the data specified. Meaning that, for example, in the simple value, the data is going to be specified in the binding file. In the URL value, the data is going to be specified in a URL address. In the context value, specifies the data. The, um, the, the data needs to be found in the computer decision support engine. And the preload value, well, as I said, it provides the ability to store the data in memory to be consulted later. One thing that we wanted to create or to do is that these values can be nested, meaning that a URL can be inside a preload value, or a context value can be inside a simple value. This provides the mediator with the ability of dynamic querying without modifying the binding file. So next, please. Okay, and next, yeah. And this is we started creating a generic data loader. This was the first loader that we created. This data loader, the main attribute is the loader URI, that specify the class that is going to be used for load the data. Any number of parameters can be specified, and these parameters can be simple or multiple. These parameters will look for the data using the value option that I already commented. Next, please. So this is an example of a generic data loader, and you can see here that the data loader type is a generic data loader. The URI will point to the class. In this example, is an XPath loader, and the XPath loader needs three parameters: the URL, the XPath, and the namespace. The URL is going to be where the document is located, so it's going to look for this document, the XML document in that path, and the XPath parameter specifies the query that is going to be used to retrieve the information from the document. Here you can see the well, ability to nest values that I already told. That inside inside a simple value is a context value that have a patient ID. This means that for each time this query is this mapping is executed, the patient ID can change. You don't need to define the mapping with its patient ID for each patient that you want. If the clinical decision support system has an ID, a patient ID, it's going to be loaded here and put it dynamically in the simple value query. And also, well, the namespace is only to avoid the disambiguation in the XML query. Next, please. So the main problem here, you can see, it's too complex to be used regularly. So the solution that we propose is to reduce the complexity of the mappings for the most common data sources that we realize. So next, please. We created several specific loaders. Among those, the XPath loader, which you already saw that need URL, XPath, and namespace parameters. Next, please. This is the code that I showed you earlier. But if you can pass the slide, please. Next. Yeah, here you can see the difference between the generic loader and the specific loader. Here it's simpler because it only the class knows what to expect, so the mapping could be simplified. And well, this is the same query as the same mapping entry as the other one, but you can see that it can also it can be understand. It's more understandable than the other one. So next, please. We also defined a web service loader that provide the ability to load from a SOAP or a REST service, but because we realized that most of the legacy systems had a SOAP connectivity, but the systems that are being developed nowadays usually use a REST interface. So why could the the ability to connect with the two of them? So we give yeah, we use the two of them. Next, please. And also we created an SQL loader. It works the same as the others. It only needs a URL and SQL to create a query. Next, please. Yeah. So I'm going to talk now about the case studies because when we developed this architecture, we wanted to know if it was going to work. So we tested first with the Proforma engine because we had already experience with that. So next, please. For those who don't know the Proforma, well, Proforma is a suite and it's composed by a language and engine. The language is provides the clinical can model the clinical knowledge in a guideline form, and the engine is enacts these computer guidelines and execute the guidelines step by step. Next, please. This is a simple example of a chronic obstructive pulmonary disease. It's a simple plan defined in the Proforma language and executed with a Proforma engine. Here you can, the diamond nodes represent the data inquiries. The circular nodes represent the decisions made in the guideline, and the square nodes represent the actions taken and the actions suggested to the user of the guideline. So when the execution starts here, clinical data is required. The guideline needs to know the data from the patient. So when the data is loaded, a decision is made. So if the guideline needs more data to give reasonable decision, is going to ask for more data in a spirometry inquiry. If not, the guideline is going to end. So if more data is needed, another request is made to another data source, and with that spirometry results, the decision is made, and a result is presented to the user. Next, please. The problem with that that we realize is that the language is limited to data sources defined internally. So, and the engine required data to be introduced manually. So, well, the solution is, I already explained, it's define an external wrapper independent of the language and able to automatize the data collection. So next, please. How do we achieve that? Well, the Proforma engine has a task adapter for each for each inquiry. The diamond node that we saw, each node has a task adapter. So we created a listener which was loaded every time the task needed data. So with that listener and with the wrapper from the engine to override the data petitions, we were able to link the Performa engine with different data sources. Next, please. So here you can see well, this is a main diagram of how the extended Performa engine work. You can see here, well, at before the guideline execution starts, the mapping file from the mediator is loaded in memory, and that mapping file specified a preload of data. So the hospital information system is consulted, and the data is stored in the cache of the CTS data, which is the intermediate memory. This allows the engine or the mediator to not create new petitions to the hospital information system each time the data is requested. So when the clinical data inquiry starts, the data petition is going to be made to the memory, to the cache of the mediator, not to the hospital information system. And the execution of the guideline is the same, but we added a new inquiry node because we wanted to test also if we were able to connect the Proforma engine with a clinical decision support system that was developed, well, that was online. So when with the spirometry data of the patient, a CDS system was consulted, and the solution of the system was passed back to the Proforma guideline. So the last decision node, the spirometry results decision, is going to be to decide, but the same as with the other Proforma guideline, but but it's going to take a more informed decision. So next, please. We also wanted to test the mediator with a generic CDSS like Curiam, and in our case it was Curiam BT, which is a brain tumor diagnosis tool. For this purpose, we wanted to connect the Curiam BT with a generic relational database. Next, please. So here it's more simple than the Proforma example because Curiam BT requires all the data in only one stage. The Proforma engine executes the guideline. Each node in the guideline is one step. Here, the Curiam BT requests all the data in one petition. So the petition is made to the mediator, and the mediator pass the petition to the database. When the result is computed, it's passed back to the Curiam BT engine. Next, please. So how do we did that? Well, the same as in the Proforma engine, we focus on Curiam is divided in three layers. and we focus on the data layer of the clinical decision support system. The data layer have a data framework that connects to the generic XML interface. So next, please. So we grab the previous one. Sorry, the Curiam one. If you, yeah, thank you. So yeah, we grab the Curiam XML interface, and we this provided the Curiam clinical decision support system with more data functionality. So next, please. Yep. And the last use case was combining Proforma with Linker. We saw that the mediator doesn't manage the data at the semantic level. And also we saw how the mediator can be connected with a semantic tool. So we tested it in a prototype for a determination of the patient eligibility. And the patient eligibility was determined by a CDSS developing Proforma, and the mediator provided a data layer that allowed the Proforma engine to access the XML documents generated by, in our case, link AHR. So next, please. Yeah, next, please. As a conclusion, well, we can say that the mediator, CDS data, provides a separation between the CDSSs and the mapping definition, the mapping from most common data sources, and easy extension to new ones. You can use the generic loader, or if you want, you only need to extend the generic loader and make a specific data loader, as we saw. Data mediate also, it provides also data mediator for the CSS, separation between raw and semantic treatment of data. Moreover, it's been evaluated in 3 successful user cases as the Proforma engine, the Curiam clinical decision support system, and a linking between Proforma and link AHR. So, yeah. Next, please. That's all. Thank you.